Good morning. In this presentation we talk about future technologies for auralization in archaeoacoustics. We start an introduction about the method and goals and where the origin of auralization were. We explain the state of the art, which currently is employing high-order ambisonics over headphones or with loudspeaker array. We will present some ongoing developments related to 3 research projects which are currently ongoing. And we see the future where we plan to have in a short time a full 12 degree of freedom rendering system, both visual and audible, where both source and listener can freely move and rotate in the virtual space. We start with the concept of an impulse response inside a room or an acoustical space. There is a source, the sound bounce over walls and ceiling and so on, and at the end it reaches the listener. All this is captured by the impulse response, which is used as a filter processing an anechoic recording. So this anechoic recording of voice or music is convolved, for example, with a binaural impulse response if a binaural microphone was employed here during the measurement or the computer simulation. The anechoic signal is convolved with the binaural impulse response. The result is the auralized signal, which is a stereo binaural signal ready to go on headphones for listening. And this is the traditional binaural rendering of an acoustical space. The software for performing this kind of processing is quite simple. Here we use an host program which is Plug-Bidul, which is a typical block and wires program. You see the blocks. The first block is an audiophile player for the anechoic mono recording. It goes to a convolution plugin. In this case we are using MCFX with 2 inputs and 2 outputs. And the output of the convolution plugin goes to the headphones. We have many possible block and wires host programs which are listed here. Perhaps there are others, but all of them, the one I favor is Plug-Bidul because it's not expensive and it is very simple to use and to manage. Very good for my students. Regarding convolution plugin, here you see a number of VST or Linux plugins which has been released in the past year. All these are free and open source. All these are capable of matrix convolution, which we will see is very important for high-end auralization. We are not considering here instead musical application like Altiverb or Waves IR1 because this plugin has the nasty feature of modifying the impulse response they are processing. Instead, for realistic auralization, we don't want to modify in any way the impulse response being used as a filter. Instead, all these 5 plugins do not alter in any way the impulse response which they use. Xvolver was the first matrix convolution plugin released back in 2005 and is capable of massive convolution with a matrix of impulse response. As you see here, this is a 4x4 matrix where there are 4 inputs, which are the columns, and 4 outputs, which are the row of the filter matrix. The one on the right instead is the convolution plugin released by Fons Adriansen for the Linux environment. This is very efficient and very powerful, and the only problem is that it only runs under Linux machine. It does not work in Windows or Mac environments. So a clever guy, Matthias Kronlachner, recompiled JConv for the Windows or Mac environment, and that is called MCFX Convolver. It's very powerful too. The only problem is that it requires a conf configuration file for loading the filter matrix. This is not practical. So we recently recompiled MCFX in a way that does not require anymore a configuration file. You can load directly the filter matrix as a multi-channel WAV file. And we also improved slightly the performance, modified the algorithm. Finally, these are plugins released by the Aalto University, the Sparta plugins, and there are two. One is a multi-channel convolver, not matrix convolution. The other is a full matrix convolver. Here you see the performance of this convolver plugin. As you see, Xvolver, the older one, was minimizing the load on the internal DSP of the host program, plug-webidul in this case, but it takes a lot of external CPU power. Oppositely, instead, the newest one, XMCFX, has a much bigger load on the host program, but minimize the overall CPU demand on the processor of the computer. So currently we think XMCFX is the best plugin for doing real-time auralization. Here we see the state of the art when applied to archaeoacoustic, so acoustical rendering of historical building or sites. In the building, in this case it is an historical theater, we use a sound source, an omnidirectional dodecahedron loudspeaker, and a microphone array. This is an Eigenmic, a spherical microphone array for high-order ambisonics capture. The result in this case is a measured impulse response with 16 channels, because it is a third-order ambix impulse response. And there is only one because this is a omnidirectional mono source. Of course, you can repeat it with different source position. The traditional way of listening is static binaural, so with just a stereo impulse response, which is good for listening over headphones or over a loudspeaker pair with crosstalk cancellation. But now, thanks to high-order ambisonics rendering, we can have headphone listening with head tracking, or we can feed a multi-channel loudspeaker array for full three-dimensional rendering, where the listener can rotate his head and still have a good spatial rendering and correct location of the sound sources. For making this high-order ambisonic signal, you need to convolve each source. In this case, we have 4 mono sources, like a quartet playing on stage, and an impulse response has been measured or calculated with a computer for each source position. So each source signal is convolved with the corresponding third-order ambisonics impulse response, and the result is a 16-channel ambisonics third-order signal. This is a 4x16 filter matrix where we have 4 sources. Every column is a source 1, source 2, source 3, source 4. And all the rows, all the channel of this multi-channel impulse response is one of the channel of the ambisonic signal. Third order in this case, so 16 channel. So this third order ambisonic signal is passed through an ambisonics decoder plugin which computes the speaker feeds, and those speaker signals are sent to a multi-channel loudspeaker array. In this example, also the loudspeaker read also has 16 channel, but of course in ambisonics you can have any number of loudspeaker independently on the ambisonics order you are playing. Here you see two of these VST plugins capable of doing real-time ambisonics decoding. The one on the left is Rapture 3D, a commercial plugin, also quite expensive but incredibly good. And on the right is a free and open source decoder called IEM All-Rad Decoder. For listening over headphones with a tracking, for example using an HMD, this is the processing scheme. We add another plugin which is a rotator before the ambisonics decoder, and the HMD provide head tracking information through the 3-axis rotation plugin. This way, the sound field is counter-rotated, taking into account the head movement, and the binaural rendering occurs employing this HRTF filter matrix. HRTF stands for head-related transfer function and converts the 16 input channel of ambisonics into the 2 output channel of headphone signal. So this is the previous scheme implemented in Plugway Bidul, and you see the same blocks. The 4-channel file player, the first convolver using the room filter matrix, then there is the chain rotator for performing rotation, a third order ambisonics decoder, a binaural filter matrix convolver, and finally headphones with OSC head tracker. Regarding head tracking, we can use the head-mounted display, virtual reality system as shown before, but you can also use a normal pair of headphones, employing a discrete head tracker attached over the headphones. In both cases, you get OSC data providing the attitude information to the chain rotator plugin. Here you see 3 examples of low-cost discrete head trackers. The left one is Waves NX, the software for it only available for Mac. The central one is the Ambient Lab MMR, which is a very compact device which only has software running under Windows. And the third one is this band, which is placed over the headphones. This is wired, is not wireless as the other two, and provide through USB OSC signal both for Mac and Windows host programs. For using an HMD, usually you employ a software which is called Vive Cinema for playing a 360-degree video or a 360-degree photos, because there is the Pan 360 version of this software, and both these have been modified by us. So you can download from my website a modified version of iCinema and Pan 360, which send the attitude data over OSC, already formatted for the chain rotator plugin. So this way you can use a head-mounted display for doing head-tracked binaural reproduction. Now we go to the 3 research projects which are currently ongoing, and these projects are Art Soundscape, Sipario, and Fe. All these projects are on archaeoacoustics, so measurement and acoustical rendering of archaeological sites. Here again we see a historical concert hall, but now instead of an unidirectional source we use a loudspeaker array capable of generating prescribed directivity of the sound source. And again we use an eigenmic as the receiver. Using an ambisonic source and an ambisonics microphone, you can measure a so-called MIMO impulse response matrix. In this measured matrix, you have a number of input channels corresponding to the directivity of the source and a number of output channels corresponding to the directivity of the microphone. Here you see our 32-channel spherical loudspeaker array. We use the Eigen mic for recording, so the raw impulse response matrix measured feeding one after the other a sine sweep on each of the 32 loudspeaker is a 32 by 32 raw impulse response matrix. From this raw matrix, you can insulate the impulse response of each of the 32 loudspeaker of the source, which correspond to a column of the matrix. Now, this raw IR matrix must be beamformed for converting it either to ambisonics or to SPS format. SPS stands for Spatial PCM Sampling, and this is a spatial format alternative to ambisonics which we have developed. For doing the beamforming, we need two beamforming filter matrix, the source beamformer for the loudspeaker and the receiver beamformer for the microphone array. Depending on the filter matrix being employed, we can convert the raw filter matrix to ambisonics format, in this example a 16 by 16 filter matrix, or you can convert to SPS format. In this example here is a 32 by 32 filter matrix with, of course, improved spatial resolution compared with ambisonics. The first project where this MIMO technique is being employed is Art Soundscape, which is a project about the acoustic of archaeological sites where there are prehistoric rock art. Sometimes is inside a cavern, like in this example, where a 12 loudspeaker array is placed, in this case, and the recording is made outside the cavern using a Zilia third order ambisonics microphone. In this way, we measure a 4 by 16 MIMO filter matrix, where the source has a first order ambisonics directivity and the receiver is full third order. Here we see an example of auralization done in real time, rotating the directivity of the source while listening to what happened at the microphone. So now we move the source. We point the source in different directions. You see here the pointer moving. Now it's pointing towards the receiver, so it's louder. Now we come back against the wall, and here you see and hear reflection. Now we go to the Sipario project. This is about Italian historical theater, and in these rooms we record impulse response using our 32-channel loudspeaker array, which here you see in more detail, and an Eigen mic as a receiver. Doing the ambisonics conversion, we get a 16 by 16 MIMO IR matrix, ambix. In the Sipario project, we not only use measured impulse response, but we also make computer simulation using the RAM7 program, which can create impulse response up to fifth order. This is another example using RAM7, which was La Fenice Theater in 98. And RAM7 creates this kind of synthetic impulse responses. In this case, we created a MIMO impulse response matrix of second order source to third order receiver, so is a 9 by 16 MIMO FIR filter matrix. We go now to the FE project, which is the third one in order of time, is just started. And in this case, we are simulating with Odeon and Ramsete programs the acoustic of the Tindari Greek theater in Sicily. In this case, we used Odeon, and what you see here is an ambisonics first order rendering of the 3rd century before Christ reconstruction of the Tindari theater. This video is on YouTube and is a panoramic video with ambisonics audio. So this movement of the camera and zoom in and zoom out, you can do it controlling the visual and audible reconstruction during the playback. You see the link here for the video. Now, we talk about auralization of MIMO impulse response, how this is performed. In case of watching the video with an HMD, we have again OSC signal going from the MHD to the chain rotator plugin. But in this case, we add another chain rotator, providing the possibility to rotate the sound source. Of course, we start with a 16-channel recording of the sound source, which already contains the directive information of the source. These are, for example, the anechoic recording made by Dario D'Orazio at the University of Bologna and made available over internet. So we can use his recording as the source for this kind of auralization. Apart the usage of a VR head-mounted display, we can also use the two listening rooms we have in Parma. One is an ambisonics room shown here, equipped with 18 loudspeakers, and it will be soon upgraded to 26 loudspeakers. This is the larger room we have, called Sala Bianca, white room, equipped with 189 loudspeakers in a wave field synthesis system and 4 beamer video projector. So also the visual rendering or the panoramic photo of the archaeological site where the recording was done is displayed all around the listener sitting in this room. Finally, another ongoing development is the usage of the Zilia 6 degree of freedom method. This approach was developed for real recording, not for auralization, where in a room during a concert a large number of Zilia microphones are placed covering all the listening area. But when instead working with auralization, you don't need to have so many microphones. You need just one. You move it in many positions, along this grid, for example, in 20 positions. And then you can use the Zilia software for this playback where the listener is allowed to move around and of course also to rotate. So the listener now has full 6 degrees of freedom. The number of position, the number of microphone defines the area where the listener can move, having a correct three-dimensional reconstruction of the sound field. Here you see an example from the Zilia website. So, as you see, the listener can move around and change position and orientation in real time. What is the future? The future add together these two technologies. So we want to have the source, which can be rotated and also translated, and the receiver also must be able to rotate and translate everywhere. This brings the number of total degree of freedom to 12. 6 for the source, 6 for the receiver. Furthermore, we don't want to use anymore an artificial rendering of the theater, of the space being replaced. We want to use photorealistic three-dimensional reproduction. In particularly, today we have this software like reality capture or mushroom, which allow from a number of photos to reconstruct the three-dimensional space and to add some sort of tiling based on the photo, making the visual rendering very realistic. For example, here you see Teatro Pavarotti in Modena. This is a panoramic photo, which was the technology used in the past, but now we can instead fly a drone inside the room and take a number of photos from a lot of different positions thanks to the drone, and then we employ, in this case, this is reality capture, for creating a 3D navigable model. As you see here, you can move inside the 3D space and look around where you want, because you have a complete three-dimensional model of the theater. Joining this with the acoustical rendering with 12 degrees of freedom, what you get is something like this, where both the receiver and the source can move and rotate. I think this explains more or less everything. So, conclusion. Today we have these nice tools available for making auralization of measured or computer simulated archaeological sites. But the future is going to merge with the video gaming technology. This both for the visual rendering and for the acoustical rendering. Using a gaming platform like Unity or Unreal Engine is possible to have a rendering either on VR technology, head-mounted display, an Oculus system or the like, but also over a normal computer, and so even on a smartphone. These make the rendering available for everyone in practice and make it possible to use the result of this archaeological research for creating video games which are perfectly reconstructing the ambience of the historical sites where the action of the game is occurring. Thank you.